Welcome to the course of analysis of several variables. So today we are going to discuss the module 1, which is some topological properties of the Euclidean space Rn. In this module, we are going to study about the fundamental recalls. So we will recall about the basic ideas which is useful for study the topological properties. Then we have introduction of Rn, then linear subspace of Rn, then basis and dimension of Rn, Euclidean inner product and norm in Rn, and then continuity of functions defined on open subset of Rn. So this six concept is consist of the model 1. So let's start with fundamental recalls about some topics. So we have the first topic is vector space. So a set V with binary operation, and we call it as scalar multiplication. Start binary operation plus additive and scalar multiplications is said to be vector space over a field F. So this field is maybe real or complex, but as we are discussing Rn, so we'll take the field F is here in this course as R. It follows following properties. So first is V is closed under vector addition and scalar multiplication. What does it mean by the close? That if you take two vectors U and V from the set V and one scalar from the field F, let's scalar is alpha, then if you take the linear, if you take the apply the operation, the vector addition, what is defined here, that U plus V, so what will be the new outcome? That should also belongs to V, means they have the same properties like U and V. And if you multiply this alpha with U, then alpha U belongs to V. So this is called the closure property of the space V. So let's have example here. Let's take B is equal C, the set of integer, okay, and F is real number, set of real number. So now we define the addition and scalar multiplication as like this: A plus B is equal AB over 3, and alpha A is equal, alpha A means usual multiplication. Then this V plus dot is not closed. Why? Because A belongs to V, B belongs to V, then A plus B, which is AB over 3. So it may not be always integer. Okay, may not be always integer. For example, let A is equal to and B is equal 5. Then A plus B is equal 10 over 3, which is not an integer. So therefore it is not closed, though alpha A is closed. Okay, so the scalar multiplication is closed, but addition is not closed. Let's have the next properties. Next property is that U plus B is equal V plus U. So it should be commutative. So for example, here we take this V equal G, the set of integer, and F is real number. Define the addition. Define the addition as A plus B is equal A square. Now under this is operation, the set is closed, but it is not commutative. Why? We'll explain it now. let's say a plus b is equal a square b, so which is always integer. If a b belongs to G. Now they are not commutative because let's take a is equal to and b is equal 3. Then a plus b is equal a square, it is 2 square, 3, then 4, 3 is 12. But b plus a, this is equal 3 square multiplied 2, so this is 18. So in this case, a plus b is not equal b plus, hence this is not commutative. Now we have next case is u plus v plus w is equal u plus v plus w. That means if you interchange the position of the vectors and rearrange it, then they must be equal, and this property is known as the associative properties. Now one of the important part is that zero vector or identity vector. So what is the zero vector? Zero vector means that for any vectors u, there exists another vector in the set V which is denoted as 0v because we call it zero vector. So you have such entries in the set V such that whenever you add any of other element of V, let's say u, then when you add the 0v, it will gives you the same vector. And if you change the position because of the commutative property, if you change the position, then it will be reverse part also give you the identity vector or zero vector. So this entries is known as the zero vector or identity. Example, we take v is equal r and set of real number, and f is also real number. Then we define a plus b is equal a plus b, which is addition, usual addition of numbers. We are not define anything special. Okay, so we just define as a number 2 plus 3 equal 5. That way we define the operation. Then 0v in this case is equal 0, the real number. As any number, if you add with 0 will give the same number, means a plus 0, with by definitions it will be a plus 0 is equal a. So this is always true. So this will gives you 0 is the number 0 is the 0 element of this vector space. Now let's define the addition is like this: a plus b is equal a plus b plus 2. In this case, 0v is equal minus 2. How it is? Because we have to get it a plus b or a plus 0v, a plus 0v is equal a. Now a plus 0v by definitions it is here a plus 0v plus 2 is equal a. So this implies 0v is equal minus 2. Okay, let's move to the now next property, which is the inverse. Okay, so the inverse is that like O0v, there exists always a one vector which you denoted as IV, such that if you take any entries of V and add with IV, then you will get the 0v. If such entries exist, then this IV is known as the inverse vector of B, and this must be true for any arbitrary vector from B. This IV should exist, then this one property will satisfy. Examples. Okay, let's have the examples here like in the previous example. So in the last example we take V is equal R, and in this case we got with usual addition and addition of numbers, we got 0 V is equal number 0. So therefore what will be the inverse of these cases? So let's, you have A belongs to R, then A plus IV is equal 0. So this implies IV is equal minus A. So the negative of any number is the inverse. So inverse for 5, inverse for A equal 5 is minus 5, and inverse for minus 5, if A equal minus 5, then IV is equal 5. But if you take this set, which we saw that minus 2 is the minus 2 is the is the inverse. So minus 2 is the 0. So what you will get here, A plus IV, so you will get should be minus 2. So this implies IV is equal so this implies A plus IV plus 2 is equal minus 2. So this will give you IV is equal minus A minus 4. So IV is equal minus A minus 4. Okay, let's have the remaining property. Property 6 is that this addition property with scalar multiplication is distributive. So alpha u plus b will be alpha u plus alpha b. So these are easy to verify. We are not going to verify. Same way, the scalar addition alpha plus beta over the vector u will be alpha u plus beta u. And if alpha beta multiply with u, and then if you exchange it, then the outcome will be same. And the last property, which is multiplicative identity, is 1u is equal u. So this all about if any set with these two binary operations satisfied this 9 property, then we called it a vector space. So you have done in linear algebra and many other courses this many examples. So we are not going to details of the examples. We just need these definitions for this course study. So similar way, we will just recall few other definitions, and next definition is linear combination. So if you have a set of vectors v1, v2, vn, and the n scalar alpha 1, alpha 2, alpha n, then the expression written as like this: alpha 1 multiply v1 plus alpha 2 multiply v2, and so on. So this expression is known as the linear combination of the vectors v1, v2, vn. So if you say w, and if you say the it is a v is from a vector space, then by the closure property, as we discussed in the previous slide, so this linear combinations which will gives you a new vector which is belongs to the vector space V by the closure properties. Our next definition is linear independence. So if you have a set of vectors like the previous one, that v1, v2, vn, and this set will be linearly independent if the linear combination, as we defined in the last slide, that linear combination is 0. So 0 here, or the number 0, 0 is the 0 vector. If it is 0, provided this all the entries are 0, C1, C2, Cn should be 0. This is 0 number, and this is, you can say, 0 B. So now if such linear combination is possible, then we say that this set is linearly independent. Next is the spanning set. Let S be a set of vectors from a vector space V. If any vector V belongs to V can be expressed as a linear combination of vector of S, then the set S is known as the spanning set of V. For example, let V is equal R, set of real number, and S is equal, the single set is 1. Then if you take that any vector of V can be expressed as the linear combination of S. Let's say 5. So 5 we can write it as 5 multiply 1. So any number, if you take 6, 6 can be written as 6 multiply 1. So therefore S is a spanning set of V is equal R. Now this set, if this set is linearly independent, then we have a one specific definition, and that called the basis. So subset S of a vector space V is called basis of V if S is linearly independent and S is spanning set of V. So therefore S is equal 1 is a basis of V is equal R. Have a number of elements, and that number is known as the dimension of V. So since S is equal 1 is the basis of, as we discussed just above, basis of V is equal R. So therefore dimension of R is equal 1. We can have many other examples. For example, V is equal 1 x square is, sorry, S is equal is x square is a basis of V is equal P2x, that is space of all polynomial of degree less than equal to 2. Okay. So therefore the dimension of P2x is equal 3. So in general, dimension of P and x equal n plus 1. Now another important aspect of this fundamental is that subspace. So we called a subset of a vector space V is a subspace if with the same operation of V, that is the addition and scalar multiplication, W is closed. That is, if W1, W2 belongs to W and alpha belongs to F, then the scalar, then W1 plus W2 should be belongs to W and alpha W1 belongs to W. You may think that it is obvious, but it is not obviously true. For example, if you have this is V and this is W. Now you take W1 here and W2. Now since W1 W2 is a member of V, so W1 plus W2, it is member of V because V is a vector space, but it is not guaranteed that W1 plus W2 belongs to W again. So if it is, then and along with this second property, then we can say W is a subspace. Means W is a vector space, or W has satisfied the closure properties with respect to the addition and scalar multiplication, which is defined on its superset V. So if it is satisfied, then it is known as the subspace of the vector space V. If these two properties are satisfied, then automatically other properties of the vector space is satisfied. So therefore W is known as the subspace of V. So therefore, to show that W is a vector space, it is enough to show these two properties. Okay, so this we finish the fundamental recall of the vectors which is required for this course. In the next lecture, we will do the next topic, which is introduction of R